In this lecture, we'll show that one can use an IMM estimator, and in some cases, it can be shown to be superior to Kalman filter for GPS navigation application. So there are some dynamic positioning applications where we are going to show this, and in order to do it, a simple procedure to generate the GPS pseudo measurements was also developed. Now, how to generate the trajectories and the pseudo range measurements? We have a user, that's a platform, equipped with a GPS receiver, which has access to the CA code, so that's the course acquisition code, but we assume it's a simple, inexpensive GPS receiver. And at time t0, initial time, the platform was at this location, moving at about 30 meters per second. So that's the origin. The platform average motion, because it is perturbed by noise, was constant velocity with a little bit of process noise in the horizontal plane, due east, then a 3 degree per second left coordinated turn that starts at 50, so this time interval is semi-closed, includes the endpoint, does not include the left endpoint, does not include the right endpoint, which is included in the next interval. This is a constant speed and constant angular rate term with the lateral acceleration of 0.15 g. Total angle of turning is 120 degrees in the horizontal plane. For the next 60 seconds, constant velocity or nearly constant velocity. Next 30 seconds, 9 degree per second. This is a pretty sharp turn, almost half a g. And again, the horizontal plane to be followed by 70 seconds of a constant velocity motion. And the actual motion of the platform is really the superposition of the above motion plus a little bit of turbulence as modeled as a continuous time zero mean Gaussian noise with components that represent uncorrelated acceleration within the x and y directions and velocity along the z direction respectively. So this is a three-dimensional problem where the motion is still in the horizontal plane. The two covariance matrix of the equivalent discrete time noise not known to the filter for the motion part is Q given by this expression, where we had the matrix V2 given earlier, power spectral densities in the x and y coordinates, that white noise acceleration 0.1 meters squared per second cube, and in the vertical motion SZ, these are velocity inputs because it's a single state, is 0.01 meters squared per second. This is the unit here. Now, the GPS receiver is equipped with a crystal clock, which receives a synchronized signal from all visible satellites every second. A sampling interval is 1, and the time constant for the dominant error component is, for the clock, 600 seconds. This is a characteristic of crystal clocks. The pseudo-range measurement from each satellite is generated with a clock state XC, that's bias and drift, obtained from this equation, where VC is white noise with covariance QC, as again described when the clock model was presented. The pseudo-range measurement W is assumed to be the sum of a first-order Gauss Markov, that is exponentially autocorrelated sequence WE, and a white noise W super W, the latter with covariance sigma square. And it is diagonal, n is the number of visible satellites, so it's across all the satellites, same variance and uncorrelated. The elements of the WE are uncorrelated, again, across satellites, so each of them has variance 3, the autocorrelated noise, and the white noise has 3 squared, and the variance of the white noise is 1. The state space models. 2 IMM estimators were used here, an IMM linear, an IMM CT, and 2 Kalman filters, KF1 and KF2, as baseline for comparison. The IMML, in a similar manner to the air traffic control problem, uses 2 white noise acceleration models with 2 process noise levels to cover the uniform motion and maneuver respectively. IMM-CT uses 1 white noise acceleration model and a nearly coordinated turn model denoted just by CT, and the 2 extended Kalman filters, really not Kalman but extended Kalman, because even the IMMs require extended Kalman. We have non-linear measurements. KF1 and KF2 each is based on a single white noise acceleration model, and these are the 2 baselines. The state space models for the IMM-L estimator and the baseline Kalman filters have the following form. That's a linear board-face X state vector, which now is X position, X velocity, Y position, Y velocity, only Z position, clock state, and then the 9 or N satellite autocorrelated noises. And the ZK measurements is the nonlinear function h of the vector x at time k plus the white noise part of the pseudo-range measurement. So what we have, the x already includes the autocorrelated parts of the measurement error. This is why we have here only the white noise. And this is why we have this 18, or that's 9 plus n dimensional state vector. And we have the expression for the measurements here. This is range, the effect of the clock bias, that's already converted with the speed of flight into a distance, because remember, these all have to be distance. So this is not a time variable, but is a distance variable. And this is the autocorrelated Markov process of the pseudo-range measurement error. So this is the function h of x. And what we have is, on top of this, the actual measurements include the white noise. We have a linearized measurement system matrix, manner completely similar as given before. You can see here the speed of light. That's because of the bias of the clock was converted into distance already. And measurement prediction is just using what amounts to first order EKF. You use the function h evaluated at the predicted state vector at time k, given the data obtained including k minus 1. And we have the covariance of the process noise. This is for x, 2-dimensional, for y, this is for z, 1-dimensional, this is for the clock. And here we have the process noise, the white noise entering into the shaping filter subsystems, which generate the autocorrelated measurement noise, which now is part of the state. These values Q are design parameters, and the value of the white noise driving those shaping filter subsystems was determined in the manner described in 1284. Now, the IMML estimator and the Kalman filters assume that the platform is in nearly uniform motion, straight and level, nearly constant velocity motion, with the following augmented system matrix. This is a double integrator, F2, F2, 1 for Z, same double integrator for the clock, and this is the first order Markov autocorrelated measurement noise, which are now part of the state. So this is a block diagonal transition matrix. Now, the Kalman filters use an artificially inflated covariance QF of the process noise to cover possible deviations from the uniform motion, such as turns. So, the KF1, KF2 use some noise that can handle the maneuvers. The state space model of the IMM-CT is similar to the above, but it has one more component, the turn rate omega. So what we have is xx dot, yy dot, omega. That describes the 5-dimensional state for the horizontal motion, z vertical, clock, and the satellite autocorrelated noise state components. The IMM-L estimator used a process noise power spectral density Q1 for the low noise model, 0.01 meters square per second cube, and Q2 9 meters square per second cube. This is the quiescent and maneuvering model, low noise, high noise, and you can see there's a big difference, and it can be related that these models correspond, the RMS accelerations are of the order of the square root of q divided by t, so that's about 0.1 meter per second squared. It's very important to be able to relate the continuous time system, and this has to be defined in continuous time because everything else works originally in continuous time, like the clock and these noises are in discrete time, but the clock is in continuous time. So what we have is also for the vertical motion, motion RMS uncertainty, again the QZ t in this case, square root of it is 0.1 meters, so this is how much the vertical motion uncertainty is over 1 second. It's a relatively small value, so pretty smooth motion. And the Markov chain transition matrix between the modes is 0.9 and 0.1 for jumping from no maneuver to maneuver, and same thing, 0.9 to stay maneuvering and 0.1 to get out of a maneuver. Also know the large ratio between these two. Unless you have a large ratio, the filter will not be able to find out what's going on, but in any case, given the fairly severe maneuvers this object can undergo, sharp turns, this corresponds to about 0.3 g. The maximum acceleration of the object was around half a g. So this is roughly between the half and full value of the acceleration. Now, the performance of the IMM estimator, as indicated earlier, it's not very sensitive to the choice of the transition probabilities, but it still provides, to a certain degree, a trade-off between the peak errors at the onset or termination of a maneuver and the maximum reduction of the estimation errors during the uniform motion. That's what we want, to be adaptive. Uniform motion, we want as much noise reduction as possible. During maneuvers, we want to keep it just below the raw measurement noise values, root mean square values, because it is extremely hard, if not impossible, to obtain any reduction during the onset of the maneuvers. The IMM-CT estimator used process noise power spectral densities 0.01 meters square per second cube. This is the linear additive noise which models the deviation from the coordinated turn, ideal coordinated turn motion. And there was a standard deviation of the turn rate process noise, 3 degrees per second square. So like in 1 second, it can assume a 3 degree per second turn rate. That's why we have this as an acceleration. And the process noise power spectral densities for the two Kalman or extended Kalman filters, denoted as KF1 and KF2, are 0.25 meters square per second cube and 1 meter square per second cube, and these are compromises between the non-maneuvering and maneuvering situations. The smaller process noise level will yield a better performance during the uniform motion at the cost of a higher error during the maneuver. A trade-off is needed in practice, and we evaluated two possible trade-offs in this case. The results that are to be discussed are based on 200 Monte Carlo runs. The RMS position of these estimators is presented in the figure to be looked at in a moment. The KF1 with low process noise clearly has a lower error during the quiescent period, but it shoots up a lot during maneuvers, and KF2 is believed to be a better compromise. So here is the KF1. It's here low during quiescent period when the target, the object, the platform on which the sensor does not maneuver but shoots up a lot. The KF2 doesn't shoot up a lot, but it's not very low in the absence of maneuvers. The IMMR is somewhere in between, more or less same level with or without maneuvers, and only the IMM-CT can keep the errors really low regardless of the maneuvers. So clearly the IMM-CT is superior because no single model, and not even the linear model-based IMM, is as good as this. The speed errors and course errors, it should be mentioned that in practice it is not the x velocity error and y velocity error, the RMS velocity error that is of most interest. It is the error in the magnitude of the velocity vector, the speed error, and the course. This is the angle in which the velocity vector is pointing. And again, the IMM estimators have better performance with the IMM-CT under 0.3 meter per second estimation error during the uniform motion and the first term. Then it's a little bit more. The second term is sharper. And we can see here again, error in meter per second, it stays pretty much constant. None of the other filters can match it. And these are the course errors. It is harder to get, it turns out, the direction in which the velocity vector is pointing, so it is pretty good under 1 degree when it's not maneuvering. When it maneuvers, it seems to lag, has a small transient, then it is about 3 degrees. It cannot catch up until the turn is finished. Nevertheless, it is still the best of all the filters. The maneuvering mode probabilities, you can see a substantially large increase in the maneuver mode here when it takes place in the IMM-CT. It really knows the platform is turning, and the IMMR does not have a very high confidence, only about 60%, and this is because the maneuvering model for the IMMR does not match the actual coordinated turn as well as the IMM-CTs, which has a coordinated turn model. Then we have a table comparing the RMS position errors. During the quiescent period, you can see that the IMMR is just a little bit better than the Kalman filters in both position, speed, and course is actually quite a bit better. In peak errors, again, it is superior. IMMR is not very good in the speed, however. You can see the IMM-CT because it has a much better, more appropriate model, the closest possible model that we can use for the actual coordinated turn. It is better. These are the average quiescent, these are during the maneuvering time, so again, it's the same ordering. And we can make a number of observations from these results that the IMM estimators and the carbon filters have about the same accuracy in uniform motion, which is fine. The IMM estimators are much better in terms of speed estimates and significantly better course estimates than any of the carbon filters during the turns. And the IMM estimators have much better position estimates than the carbon filters during the turns, except from the very beginning and end, at which they are about the same. It should be added that the assumption was here that all we get is pseudo-range measurements, not delta range, because delta range is Doppler, and the big improvement here is especially in the speed. Now, if you have also Doppler, which amount to velocity measurements, there will not be much of a significant difference between the IMM and Kalman filter. However, if the desire is to obtain acceleration estimates, then still the IMM will be better in estimating acceleration, because this is one derivative beyond what the measurement provides directly. And the assumption was also here that there is no inertial navigation. That's a GPS only, which is extremely inexpensive. So it's like for a simple land or water vehicle for civilian use, which does not have inertial navigation, because this is significantly more expensive. The integration might not be expensive, but the components, the maintenance, the cost and maintenance of the inertial navigation components is several orders of magnitude more than what a GPS receiver is. So again, this is useful when you have a significant maneuvering index for the target and you don't have direct measurements of the velocity. You get better velocity, and it can be used similarly for acceleration if you do have velocity measurements, because now with delta range one can obtain pretty accurate velocity measurements.